All right. This is work by Peter Sunehag in collaboration with Marcus Hutter. Unfortunately, none of them can be here today, and they've asked me to present it. I'm a PhD student at ANU of Marcus Hutter and spend my days proving things about AGI. All right, so this title is actually about optimistic agents. I'm going to try to give you some context first on this work. So we're dealing here with general reinforcement learning. You're all familiar with reinforcement learning, and in this line of work, we're not making any assumptions on the environment except that it's computable, right? No Markov assumption, no observability, none of that. And I'm shamelessly plugging some of my own work here. So recently, we had some results on AGI's lack of optimality. So right now, there is no objective notion of optimality anymore that we know for AGI. So whether AGI is the perfect agent, as Benya already put into question, yeah, but there's a solution to this, and the problem really is lack of exploration. And you can add knowledge seeking to AGI, or you can act optimistically, and this is what this line of work is about. So I'm going to be talking about optimistic agents. So first, I'll give you some background. Let's take a finite set of deterministic environments, and then we're going to act optimally with respect to that set, meaning we'll pick that policy that will give me the highest reward if the best environment from that class is actually the true environment. And I'm going to follow that policy until I arrive at a contradiction and I falsified one of the environments. And then I can go on to the next environment and so on and so on. And I get this bound that the number of epsilon errors is less than this quantity. So it's basically linear in the size of the environment class. And you can also grow the environment class. So if you have a finite environment class, then you're not really as general as we'd like. But if we can make this a growing class by just introducing new environments every time, every once in a while, and then we have to re-pick the policy possibly. And if my true environment eventually gets introduced, then I get this bound on the number of epsilon errors, which is, again, linearly dependent on the number of environments. And this linear, and importantly, if I do this, I'll get a weakly asymptotically optimal agent. So basically, this optimism gives me an added exploration so that I can fulfill this objective, non-trivial optimality criterion for general reinforcement learning. And currently, this is the only optimality criterion we know. Okay, so this linear dependence on the environment class is annoying because, generally there's a lot of possible environments. So how do you make this more efficient? And the idea here is that instead of considering environments, we will consider laws. And laws are basically partial functions that predict some or all of the features that I'm going to see under possibly some circumstances. So partial prediction is what Peter calls factorization, and you don't have to predict all the time, you predict sometimes under some circumstances. That's what he calls localization. For example, you have the deterministic law of Newton's 3 laws of motion and gravitation, and then you get this mechanical universe. And you can kind of picture the agent puzzling together its world by the use of different laws that predict different things in different contexts. And every time you find a contradiction to one law, you can contradict a lot of environments. And the good news is then we can look at the previous error bounds that were linear in the size of the environment class, and now they're only linear in the size of laws. So if I have some set of laws, I can generate exponentially many environments from them. So basically, we've sped up we've improved the bound by an exponential amount. So the thing is that the real world is not deterministic, or not in the way in everyday life. So what is new in this paper is that this is generalized to the use of stochastic laws. And stochastic laws are more difficult because you can't just contradict them. For deterministic law, if you find one instance where it doesn't hold, already you can throw out that law. For stochastic laws, you can't do that. You can just reduce your belief in that particular law. And what you then get if you make a dominance assumption, you get that the stochastic laws merge with the truth, which is just statistic speech for saying they'll converge to the right thing. And in background in previous work there was Peter considered a stochastic background environment that you add deterministic laws on top of. And now, with these new results, we no longer have the need for a stochastic background environment. We can just use the stochastic laws directly. For example, if you want to think of an example of stochastic laws, you can think of CTW, where you break up every context to get a different law. Okay, so ideally what we want to do is we want to mix stochastic laws and deterministic laws. Because deterministic laws, if you have some determinism in your world, deterministic laws are really great because they're so easily falsified. But if you only use determinism, then if there's some noise in the environment, that just breaks the agents because all the laws just, many laws just get falsified quickly. Okay, so our new hypothesis law is a mix of deterministic and stochastic laws, and as the deterministic laws fail, we fall back on stochastic laws. And you can kind of view the deterministic laws as learning by exclusion. I exclude the deterministic laws that I know are false, and the stochastic laws are learning by merging. My Bayesian posterior converges to the truth. And the kind of punchline of this work is that if you combine stochastic laws with deterministic laws, then this is highly beneficial if some aspects of the environment are deterministic and others are stochastic. No. I just wanted to leave the punchline there for a moment. Okay, so the conclusion. So we started with axioms of rational reinforcement learning. Oops. Sorry about that. And we defined optimistic reinforcement learning agents. This is general reinforcement learning, no Markov assumption or anything. And we can give error bounds, and they are linear in the size of the environment. And in order to speed this up, or to improve this bound, we use localization and factoring, where we use these laws to predict some of the features some of the time, and then construct our environment class by combining several laws. And in this paper, we added stochastic laws. And the whole combined work is just coming out as a journal paper that I encourage you to read if this is interesting to you. And Peter has actually moved on. He's now at Google DeepMind. and he uses deep reinforcement learning to do some YouTube recommendation stuff. If that's interesting to you, and you have some background in computer science, math, statistics, machine learning, deep learning, reinforcement learning, like the cool things, you should email Peter. But if you like mathematical theory and thinking about ICSI and Solomon induction, Marcus Hütter has also has a new postdoc position. Yep, that's it.